Welcome to another fun-filled edition of Comet Algebra. This video is for Algebra 1, Chapter 11, Section 2, Simplifying Radicals. All right, not much of an explanation for this, except to say that a radical is simplified in its simplest form when there's no perfect powers left under the radical sign, when we take out all the perfect powers. It's kind of like simplifying fractions. You just keep taking out common factors until there isn't any more to take out. Like first example here, square root of 24. There are some perfect squares hiding in 24, and we just have to find them. Sometimes after you have done this a while, you'll start to see them, which is another reason why I'm having you memorize these perfect squares. But I'm going to show you a method that always works no matter what. It's like your ace in the hole. You can always use it. Remember those lovely factor trees we did when we were finding GCFs and different things? Well, factor trees will never let you down when you're looking for perfect roots. Now you'll notice this is a square root problem, so we're looking for perfect squares. 24 is even, so the first prime, of course, is 2. 2 times 12, 2 times 6, and 2 times 3. So now since this is a square root, I'm looking for pairs of primes over here in the factor tree, and I'll usually circle them to make this really clear. So we have a 4 that's the perfect square, and what's left under the radical is any of these leftover primes. So since another way to say this, that 24 is equal to 4 times 6, this 4 is the perfect square that's hiding in the 24 that we need to take out. And the factor tree gives you the square root of 4 in case you don't know it. So the square root of 4 comes out and has to live out in front here because we have done the perfect square of 4. The perfect square of 4 is 2. So the 2 is now out in front of the radical, and the 6 is left behind. So the simplified version of square root 24 is 2 square root 6. Moving on to the second example, 75. Again, if you didn't see it, you could do the factor trees, and I just noticed that 5 went into there evenly. And 15 is 3 times 5. Again, square root, we're looking for pairs. Here's a pair, this 5 and this 5. So there must be a 25 and 75, which of course there is. It's 25 times 3. The 25 is the perfect square. I'm not going to require you to write this step. I'm just sort of being a little Captain Obvious here and showing you that 75 is 25 times 3. 25 is a perfect square, so that perfect square has to come out because the square root of 25 is 5, and all that is left behind is the square root 3. So square root 75 simplified is 5 square root 3. Now, cube root. This is where a factor tree is going to be, I think, extremely helpful because we're simply not used to looking for perfect cubes. You're going to get pretty good at looking for perfect squares, but again, I just don't think we're going to find a better method. Since it's a cube root, we're looking for 3 of something. This is a perfect cube. And if you want to know what the cube is, it's 2 times 2 times 2, which is 8. So again, I'm going to be real Captain Obvious here and write this as 8 times 5. This is a perfect cube. The cube root of 8, we will do that cube root, and it will come and live out in front. The cube root of 8 we found is 2. So this becomes 2 cube root 5. So here we have in words that process that we were just doing. To simplify radicals, you are searching for any perfect roots that are under the radical, and you do so by looking at a factor tree to find perfect squares or perfect cubes or perfect fourths, whatever the root is. You bring the perfect powers out in front of the radical sign because you've done that root. And if you have more than one factor out in front, you do multiply them. If you're left with more than one factor under the radical, you do multiply them. This is all connected by multiplying. So we'll have to look at some examples where we end up with more than one factor in front of the radical and underneath. Now we want to have our factor tree method ready to go because, like I said, it'll never let you down and it'll always show you the perfect squares or cubes or whatever. But sometimes you can skip that step if you happen to recognize some of these squares. So if you're looking at 45 and you know off the top of your head that 45 is equal to 9 times 5. Now, the danger with this, of us seeing a perfect square, is that sometimes we won't see the largest one, and we'll have to do this step again, but that's okay. I just want you to see this, that 45 is 9 times 5. This is a perfect square. The square root of 9 is 3, so the 3 comes out in front. The 5 stays under the radical because there's no perfect squares left in the 5. And if we had done the factor tree, we would have gotten the same thing. 288. Some of you may see, if you know your times tables a little bit and you know what 12 times 12 is, you might have seen that already. But let's look at maybe both ways for this example. So I'm going to do the factor tree very quickly over here. Something kind of special happened when I started this factor tree. I saw that 288 was an even number. I divided it by 2, and then I saw this. I have 2 times 144. And again, we want to be able to recognize perfect squares because it's going to make your simplifying of these so much easier. This is a perfect square of 12. 144, square root 144 is 12. The 12 comes out in front. The 2 remains behind. And now it's simplified. The cube root of 135. I honestly am not seeing it. So I'm going to do the factor tree. So I got 3 times 45. 45 also has a 3 in it. That's 3 times 15. And that has a 3 times 5. Remember, this is a cube root problem, so we're looking for a perfect cube or a set of 3. And we do have 3 primes here. So 135 has this perfect cube in it of 3, so the 3 comes out in front, and it is the 5 that remains under the cube root sign. Now, since I did not do the factor tree of 288, when I saw that there was a perfect square of the 144, now I have to do it because I certainly can't see a perfect fifth root. I just don't know the fifth roots. So I'm going to take a minute and do this factor tree, and I'd like you to do the same. Now, of course, use your calculator and just keep dividing by 2 if it stays an even number. Okay, wow, that's some factor tree. Coming back here, we realize that we have a fifth root here, so we're looking for a perfect fifth, or a group of 5. And we have a lot of 2s, so let's see. 1, 2, 3, 4, 5. Here is a perfect fifth root. And so this 2 comes out in front, and what stays under the fifth root, there's 2 things left behind, this 3 and this 3. Remember, we said that they're connected by multiplying. So you do the 3 times 3, and you get 9. So the simplified version is 2 times the fifth root of 9. All right, likewise with 48, we're looking for a perfect cube, and we're just not good at recognizing cubes. So I'm going to use the factor tree so that I don't miss anything. Third root, so I'm looking for a group of 3. I find them. This 2 times 2 times 2 is 8. Anyway, the perfect cube is a 2, so that comes and lives out in front. And what's left behind is this 2 and this 3. And 2 times 3 is 6. So that's the simplified version for number 8. And I'm going to kind of like this here. This is nice. I can use the factor tree for the 48, but I realize I'm not doing the third root this time. We have a fourth root. So do we have a group of 4 over here? Yes, we do. I'm going to circle these 4 2s because that is a perfect fourth. So that 2 comes and lives out in front, and underneath the fourth root, we still have our 3. So the fourth root of 48 is 2 fourth root of 3. All right, now let's look at example 10, because of course we have to start doing this with some variables in algebra. X squared is a perfect square, and y to the fourth is a perfect square, and I'm going to kind of show you why. Well, I hope the x squared one is easy. But the y to the fourth is a perfect square because it's an even power. And we can write this as y squared squared, because we know that when we have a power to a power, it's 2 times 2 is 4. So this is a perfect square, which is just x. And this y squared squared is a perfect square. So this square root takes care of this exponent, so I'm left with a y squared. Another way to say that is the square root of y to the fourth is y squared. So those were both perfect squares. We no longer have a radical in our answer. Now in number 10, I said something that I hope you caught. Any letter with an even exponent is a perfect square. And that kind of doesn't make sense to our brains at first, because we think that, well, y to the fourth is a perfect square because 4 is a perfect square. But there's more to it than that. Did you know that y to the sixth is a perfect square, even though 6 is not a perfect square? It's because it divides by 2. So let me write this as y to the third squared. Think about that for a minute. This square root undoes this square, so the square root of y to the sixth is y to the third, again because it divides by this root. So y to the seventh is not a perfect square, but I'm going to go down 1 power to the first even one that I can find below 7, which is 6. So I'm going to break up this y to the seventh into y to the sixth times y. And then, just to repeat what I wrote over here, whoops, y to the sixth is y to the third squared. And this is a perfect square. The square root of y to the third squared is y to the third. So that comes and lives out in front. And what's underneath the radical is just the y. Okay, now looking at example 12, we got to sort of shift our thinking now that we're looking for cube roots. And this negative sign really is a -1, so we just want to treat it like its own factor. So I have a -1 here. And again, since this 6, this exponent of 6 divides by 3, a to the sixth is a perfect cube. And I'm going to try to be very obvious with you to rewrite the 6 as 2 to the third power, just so that you can see the perfect cube, and quite obviously b cubed is a perfect cube. So this is a perfect cube, this is a perfect cube, and this is a perfect cube. We're going to have nothing left under the radical sign when we're done. The cube root of a -1 is a -1, so we'll keep that negative sign. The cube root of a squared cubed is a squared. And the cube root of b cubed is b. Nothing left under the radical. All right, this next one, 121. So shifting your brains back into square root mode, because this is a square root symbol. Again, you could do the factor tree, but if I have done my job and kind of made you memorize the perfect squares, you realize that 121 is 11 squared. X to the eighth, 8 does divide by 2 evenly, so we know that x to the eighth is a perfect square. But again, I'm going to be very obvious and write it out for you. It is x to the fourth squared, because a power to a power, we multiply exponents, and we would get x to the eighth. This y to the fifth does not divide by 2, so it is not a perfect square. But we're just going to bump down to the next even number, which is y to the fourth, which is a perfect square. So I'm going to write it as y squared squared. And because I had a y to the fifth, I do have this one y that's left over. So now this is a perfect square, this is a perfect square, as is this. The only thing that's going to be left under the radical is that y. The square root of 11 squared is 11. Y to the fourth squared, the square root of that is what? I'm sorry, x to the fourth. Y squared squared, square root of that is y squared, and what's left under the radical is just the y. All right, 108. I'm going to need a factor tree, so I'm going to pause it and do that off to the side here. All right, so number 14, we are looking for perfect squares. It's the square root. I made the factor tree here, so we're going to circle pairs. Here's a pair of 2's as a perfect square and a pair of 3's. So again, you're not always going to write this step. I'm just doing it for your notes to be very obvious. So we have 2 squared is a perfect square, 3 squared is a perfect square, and this 3 is just left over. Continuing on with our variables, x squared is a perfect square. Y to the 7th, we go down to y to the 6th, becomes y cubed squared, and we have that leftover y, and that z is nothing I can do with it. So I'm going to underline the perfect squares just to be as clear as I can, and that's what needs to come out in front. So the 2 comes out in front, the 3 comes out in front, and you go ahead and multiply those. 2 times 3 is 6. The x comes out, the y to the third comes out, and everything else needs to stay under this radical sign, which is this 3, and this y, and the z. So that's your final simplified answer. All right, this last example just looks plain old frightening, such a large number. But just grab your calculators and let's do the factor tree for 1,715. And since it ends with a 5, I'm going to divide mine by 5, and I got 343. And I kind of remember this from the last section. I'll just help you out here. This divides by 7. You know, you would check 3 and check 5, and just keep checking primes until you found one. And now it doesn't look quite so scary. We notice that we have a cube root problem, so we are looking for a group of 3, and we found them. So again, I'm going to be really obvious here, and pretty soon you can skip this step. We have the perfect cube of 7 to the third. The 5 is going to be left behind. A to the 4 does not divide by 3, so I got to go down to the next one that does, and I find it's a to the third times a. I kind of broke up this a to the fourth. Do not need to break up that b to the third because that is a perfect cube, but I need to break up this c to the fifth into c to the third times c squared, and now I'm going to underline the perfect cubes that will come out in front, and the rest will stay behind. So the 7 comes out in front, this a does, the b does, and the c does. And the things that remain under the third root sign are the 5, the a, and the c squared. Okay, that problem wasn't so bad at all when we just broke it down into its perfect cubes. All right, now you have the knowledge you need to simplify radicals, so have a radical time with that.